right. Hello, everybody, and welcome back to the Tom Lonnie Chat. I'm Tom of Tom and Lonnie, and I think our good friend Dr. Lonnie Love is not available today, but we thought let's get this podcast out. We owe you guys, we owe you out there in podcast land a new podcast, and so let's get it out to you. And today we've got, let's see. Well, first of all, of course, let's bring our friend Stephen LaMarca on from AMT. Hey, Stephen.
Yes, sir. What's up, Tom?
I'm Tom. You're looking good. You got the matching shirt with the microphone and the whole bit, and you're coming through, wall to wall over here. So
thanks. And
then let's see. We've got our guest today, Dan Skulan from Renishaw. You can tell because he's got Renishaw written over there on his little jacket there. Dan, welcome. How are you?
I'm doing fantastic. I'm honored to be here on your podcast today. So,
all right. Well, so I tell you, I was sitting in a set of meetings. I don't know. This is probably a couple of months ago, I guess, Dan. Right, and Dan
Sure.
was showing us some cool stuff. Which you see some of the stuff happen in the background, right behind him over there, over in his center. But he was showing us some pretty cool stuff, and I was like, wow. We need to get this out to the Tom Lonnie Chat, to our audience out there, to see what's going on with stuff that nominally you can do with your machine tools. So I think what we'll do is we'll just turn it over to you, Dan, and chat
Sure.
a little about some cool stuff and where things are going. Maybe maybe you'll give us a sneak peek or preview of what's going to happen over at IMTS. We're 5 months away. Is that right?
We are. Yeah,
Very
and I'm
cool.
really looking forward to that. There's definitely some cool technology that we can show. So yeah, thanks for being here, for allowing me to be here. We are in Renishaw's race facility, which is our application center of excellence out of Auburn Hills, Michigan. I thought it'd be kind of cool having some technology behind us. But for those that don't know Renishaw, we're kind of a household name in the machining world for quality and inspection and process control. So interesting technology started about 50 years ago with the development of the touch trigger probe, which allowed automated inspection on CMMs and on machine tools. And from there, the company has progressed to engineering-oriented company with many technologies that enable advanced manufacturing. And the talk that you were talking about, Dr. Kurfess, was at Georgia Tech and Internet of Things for manufacturing. And then we did a showcase with some large aerospace companies looking at complete process control and really looking at traceability in manufacturing operations. And a key point that we bring in, and this is not about Renishaw technology necessarily, just about in industry, the whole move toward automated manufacturing and intelligent manufacturing, the use of AI. I sat through your Chat GPT talk, and I found that fascinating. Without having fundamental truths, these large language models and these AI engines can really run amok. And when you're doing precision manufacturing, something that we fly in or that we drive in or is implanted in our bodies, we don't have room for making up stories and saying, oh, well, let's complete the sentence this way. That's great. Let's add a few micron here or a few thou over there. What's form? Well, form is the figure of a woman. No, it's not. Form is the form of a part inside of an engine that is making this plane fly. So fundamentally, that's what Renishaw does and what we're about. So I'm hoping to give you guys some information that the audience can use, your viewers can use directly in their shops. And Tom, you and I talked about that you have a wide audience of people. Most companies that do CNC machining are familiar with Renishaw technology, probing systems on their machines, calibration, and the like. So I wanted to show you guys a couple of technologies that I think the users could use. And I'll say that in my position, I've been in this industry about 40 years, started out in engineering, and then I'm now general manager of industrial metrology for Renishaw in the US and the Americas. I get the luxury of going out to hundreds, some years thousands, but hundreds of companies and helping them deploy technology to automate and to increase the intelligence of manufacturing. So I can share, glad to answer questions that you guys have, but share with you what we see. I guess see me as a man on the street going into a lot of these different companies, and like to share with you some of the wisdom, some of the insights that we've learned working with other people and the things that we've developed ourselves. So any questions on that first off, and then I'll get into some of the technologies.
I think we're good unless Stephen has something. I mean, but the one thing I do want to point out, and we talked about this last time with ChatGPT and so forth, and Dan, you're right on the money. So the one thing that AI needs, is data. Well, I get, I was speaking, the word data are plural, right? So it needs data sets, maybe.
Yep.
And so that's really what we're talking about. And to me, it's sort of, it's kind of like, show me the money. Okay, this part is good. Okay, show me the data that say it's good. I took my micrometer, I made the measurement, my plug gauge, whatever it might be. And so this is taking a look at, how do you do that? But simultaneously, how do you also store those data and so forth to make sure that, down the road, if you need to recall them or you want to use them for something else and so forth, they're available. So it's really, there's a lot of cool stuff going on, but it's really, this is something that people should be comfortable with, but you're looking at it now from a whole different perspective, and there's a whole different value proposition. So
sure,
I'd say fire away, Dan. Let's see what you got.
Yeah. So when we're talking with companies that are doing work in precision manufacturing, let's first of all see if I can get this screen to share for you guys. Share screen. Okay, Ramia, you're going to probably edit this out because, quite frankly, it's not doing what it just did for us 15 minutes before the show. So, are you guys seeing my screen?
Not yet. Ooh, now we see. Yeah, we actually saw something come up there.
Let's try that.
Yep, there you go.
Yeah, perfect.
Okay, so first off, I want to share with you a quick case study in our manufacturing. So Renishaw makes all kinds of technologies that are used for automated manufacturing and intelligent manufacturing, but treat this as if you walked into a company and you were looking at their manufacturing operations. So Renishaw does not sell this technology. We use our own technology in our manufacturing, but this is a case study of something that we call RAMTIC, Renishaw Automated Milling, Turning, and Inspection Centers. So these are based, it's our own design technology, but based on a Mazak 4-axis machine, 3-axis plus an A-axis table. And we do milling, turning, and inspection directly on the machine. So basically, raw materials come in and the machine checks itself, sets itself, tools and workpiece, does in-process control to control variation for tool deflection, the raw material change in size and form, thermal variations are all compensated real time, and final inspection with full traceability, the parts come off the machine. So we make the majority of our prismatic parts using this. Again, this is not something we sell. This is just our own manufacturing. So we'll take you inside of the machine here. First, we'll do a ball bar test, which allows us to establish the baseline of performance positioning. Probe comes out, we check an artifact that's been checked at 68 degrees, so we know what it is at temperature per standards. Tools are set automatically for length and diameter. Raw materials are brought into the machine automatically. The probe sets the work offsets, all automatically in cycle. Cutting commences, and after cutting commences, we can come back in and validate. We use something called gauge cutting, where we cut, measure, update, and then cut. We use in-process checking to make sure tools haven't broken, and then at the very end, the parts are measured in the machine. And because the machine was calibrated in advance, and we checked an artifact of known traceability in advance, every part that comes off the machine is traceable as if it were on a CMM. We get about 120 productive hours per week in these manufacturing operations, 24-hour unattended operation with less than 0.3% scrap. And I say that we have 100% quality yield. Any scrap is caught in process and we destroy the part before it goes downstream because the cost of quality is much higher than the cost of the part. So OEE pushing 90%, typically in the 85% range. And we have a ratio of machines to operators of 12 to 1. So one operator going in the factory and managing 12 machines. I visited Renishaw prior to coming to work here. I've been here 28 years. I was a user of their technology in the CNC area, and I said, I got to go see this company. And I went over, and there were two guys sitting in a room with 40 machines, all machines running. And in our talk, one of the guys said, oh, hold on a second. Light just came on, walked over to the machine, pressed a couple keys, fixed something, came back, sat back down, and we talked for another couple hours without any intervention from anyone in the shop with 40 machines running. So very impressive operations. Again, bragging on the company a little bit, but I'm not bragging because I work here. I work here because I went and visited as a user of the technology and realized, wow, this company's really got some very switched on kit. So that type of work, what we're showing there, is not for everyone, but it is indeed what a lot of companies are moving toward. So if you look here, and I mentioned that I spend a lot of time going in from a consultative standpoint, helping companies. Typically, this is what we see: a mix of different machine make and models, very skilled operators standing by the machine, sometimes more than one operator standing by the machine, trying to determine the cause of an issue. So very high labor cost, very low efficiency. The parts are stacked by the machine. There's good ones, there's scrap ones, and then there's a whole bunch in those yellow bins that are unknown. And typically what happens then is those accumulate and they get carted over to a separate room with a CMM or a measurement device where they sit and soak temperature overnight, and then they are measured, and a determination is made whether they rework them, they scrap them, or they just ship them as it is. And so these operations tend to be very inefficient. And what many companies are moving toward, and what I just showed you inside of our own manufacturing, is this type of a model, an intelligent automated factory. And I want to make sure that people know that we're not suggesting that people can invest all this money right away, but the tools that you use and the vision of where you're going can help you make incremental moves in your manufacturing operations to get to the point where, yeah, at some point you can be running with 12 machines with one operator. So the goal here with this type of automated manufacturing is to, first of all, reduce the reliance on just manual labor. That doesn't mean we're replacing people. We're just moving people from being a motion mechanism to being the brains behind the operations, which then, because you're amortizing the cost of these really skilled people over the equipment that you have, lowers your overall labor costs. One word that we say inside of Renishaw, our president coined this, is that automation can make scrap at unprecedented rates without process control. So as you start to automate and you move toward robots, for example, and robots are very affordable these days. You can use robots to tend a machine, but unless you have process control, you can produce scrap at unprecedented rates. I attended a robotic conference out in California, and they were asking, people on the panel, what are some of the things that you consider when you're implementing automation? And the first thing I said is, get the cell phone number of the person you replaced, because you don't know everything that person did. And when you think that you're replacing them with a robot because they just moved the part from point A to point B, you're forgetting the fact that this person was listening to the machine. They're holding a hand on it, feeling vibration. They're feeling the coolant. They're smelling the coolant. They're doing all kinds of things in the operation that you have to replace with direct process control. And so if you keep going on here, this type of a manufacturing environment, if you have direct process control with automation, is highly efficient, but it's also scalable. When COVID hit, companies like Renishaw that had this type of control, we could shut down individual cells because we had identical cells making product redundantly. And if we have 10 cells making the same part, each one automatically, and we have a 30% reduction in demand, we shut 3 cells down. Same people running. We don't need to do anything with manpower. It's just a matter of turning them off or turning them on. On the other side of the spectrum, our capacity needed to grow. We placed 40 machines that were identical to our operations in England over into Miskin, Wales. And those machines, from original concept to implementation and full production, 3 months, 40 CNC machines with full automation and full volume, by simply just copying at the exact same format that we had. So that is really what we're seeing going on in the industry. So how do you get there? Well, first off, looking at inspection at the very end of CNC operations is a painfully expensive way to ensure quality, because all of the value is already in the part. You have done maybe up 10, 20, 30, 40, 50 multiple operations on this part. If you check at the end, you've already put all the value in. And if you determine there's a problem, then you're scrapping not just the part, but all of the value was put in there along the way. There's also a delayed response because you are potentially having that part set, waiting for your measurement system, your operator to be able to measure it. And so you might be hours or even days before you determine you have a problem. And all that work that's been built that's in queue is potentially running at risk. And it's really difficult to look at the final product and see, if you had a final cut, what happened with the roughing cut prior to that, because you've already removed that material. In many cases, what we see when we're working with companies that are having problems in manufacturing and they want to increase their efficiency is they're looking at the final passes rather than looking at the initial roughing cut. If you're removing roughing stock and you're supposed to bring it down to where you only have a 20 thou depth of cut for your final pass, but your roughing tool is wearing out and you're leaving 40 thou, and then you're breaking your final tool and you're having poor finish on there, a lot of times that's overlooked. And so we see a lot of people chasing their tails at the end of the line because they didn't look at what happened at each stage of the operation. So what we profess, and this is something to be deployed regardless of the technology you use, is putting checks and balances in before, during, and after each operation. And this could be hand tools. You could come in right after op 10 and check things before they move to the next op. It could be probing system directly on the machine, building that information directly into the machine, or localized measurement systems such as an automated gauge or even a coordinate measurement machine that exists between the operations. And from there, you can preserve the value that you get at each stage, immediate response to problems, not only manually because you would have a view of it, but ideally, in order to capitalize on this move toward intelligent manufacturing, we need to have accurate, actionable information that's fed digitally at each one of these stages of the operation. From there, you can do direct process control. And if you want to look forensically at a whole system and whole operation, you can go back and look at, that happened in between this operation and that next operation. And a lot of times you need to tie in information such as bay doors in a building. I had one company that was experiencing problems every morning. They had rejects in their manufacturing. It was a medical device manufacturer, and spent the night in there in the plant and looked at it. And every morning at 6:30, the FedEx guy came and opened up the bay door right next to the Swiss turning machines. And the temperature dropped in the winter by about 40 degrees for a period of 20 minutes. And so it took another 40 minutes for it to catch up. But for that hour of time, they produced almost exclusively scrap. And it was all having to do with an interaction that was taking place at one stage of an operation. So to work with people and to give people a way, kind of a system to go through, Renishaw uses this, and it's readily available. There's all kinds of material out there. Myself and others have published content on this, but something called the productive process pyramid. So in any manufacturing, really in any operation, but we're talking CNC manufacturing almost exclusively here, we break down any work that you do into 4 stages. The bottom of the pyramid is the foundation. That is, what is the capability of the equipment? Those are things that you do in advance of any tool cutting any piece of metal. So it's your environment. It's the installation of the CNC machines. Are they on the right foundation? Are they anchored? Has the machine been calibrated? Is there some methodology for calibration to be ensured? So then the next stage up is process setting. That's where you're automating tool setting, work offsets on the machine, coordinate rotation shift on parts on the machine, where that machine can actually set up a workpiece and the tooling in place. Next step up, in process control. So that's where you're taking measurements in process with the intention of controlling variation, tooling variation, workpiece, part deflection, temperature, things that take place over the course of a day, over the course of a shift. And the final stage, post-process, is where you're doing a comprehensive evaluation of the final part. Now, you notice, just like a pyramid, the process needs to be built from the foundation. And it is, I can see a company that's going to fail in implementing all of the digital smart manufacturing technologies, of which there are fantastic technologies out there now. But when a company comes in and says, hey, I want to get data. Well, that's the wrong thing to look at first. The first thing to look at is, do you have a stable process that can give you accurate, actionable data? When you have that in place, then all of a sudden the data is good. I'm working with a nameless, large global aerospace company that has been collecting data for decades. They have data oceans. And one of their data scientists told me it's completely worthless because it's not time-stamped, synchronized, and traceable to any calibrated reference. And so the thought that, hey, we're just going to collect a bunch of data and just fill up servers with data, it's meaningless unless the information is traceable. And that starts with this process foundation. I'll show you one more thing, and then I'll kind of stop my screen and we can have a little dialogue, and then we'll talk about a couple other technologies. But one technology that I think is really important for people to use it for the baseline of performance is a ball bar. And a ball bar, and let me just go in here, looking at this. This is a device that is used by pretty much every machine tool manufacturer and every machine tool service organization, and most end users of CNC machines have these devices. And this device allows you to check the volumetric positioning accuracy of a machine in about 15 minutes. And from there, you can determine what the base capability is of the machine. We have many companies that use this as a device to determine the process capability. And at a very basic level, you may have 4 machines and you're producing, you want to know whether to put fine work or rough work. You can grade your equipment without doing any maintenance, any work on them at all. You can just say, oh, that's my 5 thou machine, that's my 1 thou machine, and that's my 5/10 machine. And so by getting a comprehensive footprint of the machine, you can determine what the capability is. But this device has been out since about 1989, and has been using artificial intelligence since then. So by looking at the shape of a hemispherical pattern that's detected using that device, we can analyze using a known database of machine conditions. We can do artificial intelligence assessment and say, this machine is out by this amount. Go and check the ball screw on the C-axis of the machine because you have a drunken ball screw. And it will tell you directly what's going on. So identifying the sources of error. You can look at this as a device to plot periodically. You notice when I show the video inside of our manufacturing, we run this monthly on every machine and we store that data digitally. And that data then, every time we run it, is accumulated and we can look at trends. So we can say at the rate that we're running, 3 months from now, this machine's B-axis is going to be will not position correctly. So we will then, or X, Y, or Z axis. What we will do then is we plan maintenance around what will, through the intelligence of this device, likely occur. So I'm show you results on a machine. This was a machine. I won't mention the name or where it was at. I don't want to alienate anyone here, but you'll see on there the plot, the data that was collected, and on a perfect trace, that would be a perfectly round circle. You can see that it's oblong and it's tilted on the 45. The software detects that and says that the number one cause of error here was squareness. Well, I'm share this with the audience that we get called in to do demos on ball bars on CNC machines all the time, which basically means we have a problem with our machine. We'd love to have you help us figure out what's going on. 90% of the time that we come in to do a, quote, demo, we find a squareness error. And 90% of the time, that squareness error is caused by the machine not being leveled correctly, which is something that can be very easily corrected. But most times, the machine is not even on an adequate foundation. So making sure the machine's on a good foundation, is leveled correctly, you can eliminate, from our experience and my direct experience over the last 30 years of running this device, probably 80 to 90% of the ongoing errors are caused by a machine that somebody did not install correctly, or after it was installed, they didn't go back in and check it. Because when a machine is first installed, over the first couple weeks, it settles tremendously. And about a month after first install, it should be checked again. And then if it holds true with periodic tests, machines will last for years. If you, however, allow the machine to run out of square for months and the first couple years, you'll be burnishing the guideways on the vertical axis of that machine over. You can take $1 million beautiful piece of equipment in a matter of 2 or 3 years, have a machine that couldn't hold 5 thou. And so I'll throw that out as a freebie to the group. This is that same machine showing you the analytics that exist from there. So showing that the number one error on this particular machine was squareness and what the contribution of error was. Down here on the bottom, you see the positional tolerance saying what that machine was able to handle as far as positioning capability within the volume of the test, in this case, which was a 1 foot, 300 millimeter sphere. So anyway, any questions on that, guys?
So I think that's very cool. And just to highlight, so the ball bar, as you said, Dan, it's been around a long time. And, the only thing it's doing is just measuring. You got the 2 balls on each end of the bar, and it's just measuring how far they're moving as you go around in a circle. And so, yeah,
it's just an LVDT that, so a linear transducer that has a ball on the other end. And those balls are round to 1/4 of a micron, so 10 millionths of an inch, and they are mounted in a 3-point magnetic cup that identifies the center line at all times. So that's kind of showing you that video of that running again.
Right. And if your machine makes a perfect circle, you say, hey, make a circle right around this center point. If it makes a perfect circle, that bar doesn't change in length at all, right? So then there you go. So there it's doing it's doing the vertical there, and here it's going to do, there's the complete circle. If your machine is perfect, you're not going to see any change, right? But of course, we all know there's backlash and so forth, and you got reversal error, and so you see all of that. The other cool thing about this is, of course, you're running it at 1 speed, but if you run it faster and faster, you see that your machine gets less and less capable because, when you're running things much faster, you're just going to lose some accuracy there.
And you can detect that. So that's one of the things you can do. You can explore how your machine reacts to different speeds, different feed rates. And the other thing I'll point out is that when you run a circle, I want to make sure people understand that you are exercising everything that the linear axes of that machine can do. And so all a linear axis can do, if you pull the way covers off the back of a machine and you look at what's going on in the axes, linear axes move back and forth. They stop, they speed up, they slow down, they stop, they turn around. Rotary axes move in a circle. They move in one direction, back in the other direction. That's all they do. And so when we move in a circular fashion, we're testing initially the 3-axis linear systems or 2 on a lathe, but buried inside of that signature are all of the potential positioning errors: backlash, reversal spikes, straightness error, squareness between the axes, acceleration, deceleration. All of those things are buried in the data. So it's not just checking a circle. That circle contains all of the error sources inside of the linear axes of the machine, and then the intelligence pulls that data out, so you can drill it down to the root cause.
Right. I mean, it's right in the money. And before I know, Steve, I saw you. Stephen took your mute off. But the other thing that I think is just great in terms of the difference between today's modern ball bar and the ball bar from the 80s or 90s, whatever, is the wireless capability. So if any of you've ever you've got an old ball bar there that's wired up, so you could imagine having, dragging wires around with you in an operation like this. Sometimes they can get tangled up and so forth. The new wireless systems are really wonderful. But Stephen, I see you've gone on mute there. So fire away, sir.
Yeah, I just wanted to say that thank you so much, Dan. I've learned a lot from this. This is really fun. I actually don't have a whole lot of experience with ball bars. I've seen them at several IMTSs now, and never thought to ask what the heck one was. But I do like to geek out about maintenance a lot, and I really appreciated the fact that there is a sort of sensor, if you would, and I know Renishaw for a lot of their incredible metrological technologies and sensors. I mean, when Mazak came out with the Integrix i100 ST. And I first geeked out about its capabilities of closed loop gear manufacturing. Yeah. And I quickly learned that all of that is capable because of Renishaw's metrological technology embedded in that machine. but it's really cool, and I appreciate the nod to early AI technology. Also learned that the ball bar was birthed the same year I was, so that's fun. But yeah, it's really cool that this was like the first peek into prescriptive maintenance, as I like to call it. Some people call it adaptive, anticipated, or informed maintenance, but like this is levels beyond reactive, preventative, condition based, and a step ahead of predictive maintenance. This is really it's crazy that this is this old.
Yep. Yeah. So like 35 years, and I'm showing here, hopefully you're seeing this video. This was launched last year, taking that same technology, larger profile, longer travel. One of the challenges that is faced in industry is the accuracy and repeatability of robots and how quickly you can set them up and how quickly you can recover. So we've adapted that same technology to robots. And over here at our race facility, and we have a cell off to my left where we've, entertained some of the largest OEMs here this week looking at this technology. But that is a ball bar sensor technology that we'll be showing at Automate, but we'll be showing at IMTS this year. And I look forward to kind of you guys seeing that. But we've also adapted probing technology to robots because robots need to have the tactile feel that a human typically has. If you're going to replace manual operations, you need to make sure that the device is repeatable and has good precision, and the ball bar allows you to do that. And you can see the trace up on the upper corner of the screen is very similar to what you would have from a ball bar that goes on a CNC machine. And then the device off on the right there with the 3 bars on it, that allows you to reset the 0, the encoder position, so you can reset the robot back to its base condition and base starting point. But we've also launched a suite of probing systems that can go directly on the robot, all wireless, and software to make sure that you have good metrology for the probe, which is something as robots are used more and more. Initially, it was just moving parts around in space, but you're starting to see robots, and Georgia Tech's doing a bunch of development on this, doing actual machining. And as you start doing that in the aerospace world, being able to have a tactile sensor on the end of a robot with known calibration and known capability is very critical.
So go ahead if you wanted to. You got some.
Yeah, let me show you. I want to make sure for a second time, but you brought up the Integrex machine and the gear manufacturing. In the gear manufacturing, we embed a probe called a sprint probe, and it's a scanning probe. And I'm gonna back up again so you can see the start of that. That's the probe right there. So rather than single point touches, this takes constant contact and spits out X, Y, Z, I, J, K values real time from the probe. So we can scan a sphere on side of the machine, and by scanning a known sphere, which is 1/4 of a micron type precision, with that sprint probe, we can do the same test that the ball bar does in process. And we have some medical aerospace customers who are doing this already. And the machines can check themselves in process by leaving that artifact out on the corner of the fixture. I'm honored to say that Georgia Tech will be getting one of these on their Mazak machine. And that sensor can be used for a tremendous amount of other techniques, one of which I'd like to share with you guys, because I think you'll find it very interesting. This is that same probe going into a tapered cup, moving around the rotary axes of the machine. And then from there, we can figure out the center of rotation. So you mentioned the 5-axis machines. One of the things that have to be maintained on a 5-axis machine is where that center of rotation is. In a digital world, it's always perfect. So when you're talking about simulated digital twins, the digital twin, when simulated, is perfect unless you can get the real machine information. So what we do here is we can measure the real kinematic location of the 4th and 5th axis of the machine, output that for simulation purposes, but improve it as well. And so using this probe in situ, we're able to take a 5-axis machine, measure its capability, and update its performance real time. So adaptive, intelligent control of the machine and operations. I'm switching the screen to see if you had any questions on that. I want to show you something that I think you guys will find very interesting. So I apologize while I zip through a few slides here. So any questions on that though?
Yeah, well, I'm telling you, some of the things that we're talking about here. So, part of it is there's some simple things you can do. You can basically measure your machine, you baseline your machine, and let's say you have a crash, or let's say something happens to your machine. You can go back and say, let me do the measurement again and see if my machine has changed. I think a lot of times people will have a crash and they don't have a feel for it. Ooh, did I hurt the machine or not? Do we have to do something with the machine? So even just something simple like this is how it was yesterday, and then let's take a look at it today. Is it the same machine?
Right.
You know, gets back to your point, Dan, in terms of how repeatable is your process. Well, how repeatable is your machine? If it's the same machine as yesterday, then you're in pretty good shape. If it's a different machine than yesterday, then you better go back and like you just made that calculation in terms of the the rotational error on that 5-axis machine. Okay, let's see if we can correct for it and so forth.
They can improve it. Correct.
Yeah. What what I'm thinking about is, okay, I think we need to have sort of several podcasts out there to really talk about the tool set station. No more touching off, kissing off on your part and so forth. Measuring whether it's the ball bar or going off on the precision sphere. I think maybe. And by the way, the ball bar is pretty cool. We might want to sit down and say, yeah, here's what the output of the ball bar is, and here's what you're getting, and here's what you're seeing in terms of some of those reversal errors.
Yeah, I would say your audience, if they're interested in those things, let us know. Love to host some discussions with you guys. I wanted to plant one seed for you if I could. So we talked about the pyramid. The base of the pyramid is critical. A lot of times people say, well, how can I measure on the same machine I'm cutting on? Won't it always tell me that the part's good? Well, the answer to that question is, how good is your machine? If you don't trust your machine to measure, why the hell are you cutting on it? So either the machine is good or it's not. And so fundamentally, we have to make sure that the equipment is capable. Then we can do all kinds of things. And I want to step you through one scenario that's very basic, and then one that I'm going to plant a seed for IMTS to show you something that's very exciting that we're doing in process control. So we talked about the pyramid, foundation, and then process setting, and we can go into more of that maybe the later podcast. That third stage, though, the process control, is where you start making a lot of money in your manufacturing operations using this technology. Very simple case here would be in lathes. So with a lathe, because of the structure, there's a lot of metal between a big machine loop between where the part is held in the spindle and where the tool is. And thermal changes in the environment can have drastic changes there. So what we do is we do a gauging cut, then we measure, then we apply an offset to the final pass and dial in. I've taken mediocre machines using this technology and held a handful of microns of size. Without this technology, you'd be lucky to hold 100 microns. And this is very commonly used in aerospace for decades, but other manufacturers, if you have a probe on a machine, this gauge cutting technology where you cut at a depth of cut, you leave a stock allowance, measure, update the tool, and do that last pass. That one thing right there is a very valuable takeaway. So know your machine is capable, and then use this gauge cutting technique to dial in for tight tolerances. Very valuable.
And I think it's very cool, right? I mean, it's not a whole lot different than how we used to set up machines and so forth, but now you're using it in an automated fashion. The other thing that'll be fun, I think people have often heard about lasering up their machine and so forth. And even that, how does that work and so forth? So we might want to think about sort of bringing you back. I know we've run a little bit over time.
We're probably over. Yeah. Cool. Let me give you a sneak preview for so this, are you hearing that sound?
Yes.
Okay. So this is a video, hopefully you can hear me talking over it, of a project we did in cooperation with Mazak, CF Martin Guitars, and Renishaw. And this is adaptive scanning and cutting. Guitars are made, every one of them is unique, and Martin makes absolutely the finest instruments in the world. And to preserve the value of that beautiful wood and that beautiful handmade craftsmanship, we're using technology to adaptively scan each body and create a unique tool path to cut the binding and trim. It's called the phrasing operation in Martin Guitars. This is, only bringing this up for you people, a sneak preview of what's coming at IMTS. We're going to be showing this. We're going to be digging into this deeper. But really behind the scenes of this is adaptive scanning and adaptive cutting that can be deployed in any industry. So I thought you guys would appreciate that as just a sneak preview of what's coming up at IMTS.
Very cool. Very cool. So I think, like I said, we're kind of out of time here, but I think maybe we're laying the foundation, no pun intended, for a couple of future opportunities. But what I would say is this is some pretty cool technology. I would definitely go check out what Dan and team have over there at Renishaw, over at IMTS, and really see how it comes together. And by the way, as he's mentioned, I mean, a lot of this technology, it's great on the state-of-the-art machines, but it's also very useful on some of your older, machines. I mean, it's not something that you've got to buy. I'm sure the people at Mazak say, no, you need to buy the new machine and the whole bit. But the reality is actually it's very useful on even older technology. And as you mentioned, Dan, this technology, some of it's been around for quite some time. So cool. All right.
Yeah, look forward to working with you guys in the future, and anything that we can do, glad to help out. So
great.
Awesome.
Thank you very much, Dan. And Stephen, as always, great to see you. And we look forward to seeing everybody next time when we'll have good old Dr. Love back as well as Cyber Kyle.
Yeah, we need to have Dan back because I've got more questions. Good questions, I promise. I wouldn't.
all right.
Nothing mean, but I'm really curious. This is awesome.
Very
Thanks,
cool.
Dan.
We're building a foundation. Thank you.
All right. Stay safe, everybody. Bye-bye.